Hey guys, I'm going to work out an example I did in class as an in-class problem set. This was number 4 on the day we did last week. The question says charge A is 20 centimeters to the left of B. A is positive 40 nanocoulombs and B is negative 20 nanocoulombs. A test charge C is brought into the fields. Where must C be located to be in electrostatic equilibrium or have zero net field? With all these problems, we need to draw a picture. A is to the left of B, so I'm going to draw one charge, label it A, and we know A is positive 40 nanocoulombs. And since it's to the left of B, I'll put B over here on the right. It's negative 20 nanocoulombs. And you have some test charge somewhere else in this field, and we want to put it somewhere so that it's pulled equally by A and B. In other words, the fields cancel each other. And if these were gravity fields, they would be falling towards A and B, but since they're electric fields, this charge C is either going to get repelled or attracted to A or repelled or attracted to B, depending on its charge. They don't tell you anything about C. We don't know if C is positive or negative, and it really doesn't matter in this case, but we'll typically assume the test charge is a positive charge, positive Q, or we can call it positive C. And to figure out where to put it, it really can be in 3 locations. Could be over here on the left, could be somewhere in the middle here, we'll call that positive Q, or it could be over here. And the way we determine which one of those 3 locations it will actually be is by drawing the vectors of the field. So if it's a positive charge, what would A do to that charge? On the left, it would be 2 positive charges. A would repel, and you would get a field strength from A pointing to the left. It would also push to the right on this charge. My deleting things from me. And all the way over here, it would also point to the right a really small amount. So based on the charge of A being positive and assuming a test charge is positive, we know the direction that the field needs to be on that test charge. And then we look at what B is doing to those 3 charges. B is a negative charge, so it's going to attract any positive test charge. So all the arrows should point towards B on each of them. And so you're going to get a charge from B that should be fairly weak over here. It's going to be to the right over here. And it should be fairly strong, getting attracted this way. And so from my picture, I then look at the 3 scenarios and ask myself, which one of these could the arrows potentially cancel out? And obviously in the middle, they both face to the right. And so regardless of what charge I bring in there, it's going to have a net field in one direction. It can't be 0. So then I look on the left and the right. Now this is where the numerical value comes into play. A is a larger charge than B, so how it repels or attracts a test charge will be greater because of its charge than B. And we know that field gets stronger as you're closer. So charge Q is closer to A and A is stronger. So we know that the field from A is going to be really big, and it's always going to be bigger than what B can pull on it because B is not only further away but a weaker charge. So just by looking here, I know that this is not a location where there would be 0 field. Whereas on the right side, if you get the distance just right, and again, we can call that distance to B, we'll just call that X. If the distance is just right, then B, even though it's weaker, could hold Q, even though due to that its field, and A would match it. So at this position, we're going to assume these arrows are equal and opposite, which means they would cancel. So now we need to set up an equation to compare A and B, incorporating this distance. The other information in our problem is they tell you this distance between the charges is 20 centimeters or 0.2 meters. So there's my picture. I've drawn my arrows, and I know that it must be to the right of B in order for the fields to cancel. And so now, if they cancel, we know the fields have to be equal, meaning the field of A, the length of the arrow, and it might be helpful to think of it in absolute value. The arrows we drew were drawn based on the charges. where guys get in trouble is they'd see those negatives and they want to put them in the equation. What really matters is how long the arrows are. So if you put the absolute value bars in there, it might be a reminder for you that the direction is already accounted for, and we just look at the number part. And our field strength equation is K, Q of the source, which on the left side is A, over the distance to the source. We'll call that the distance to A. And on the right, you have K, the charge of the source, in this case B, and the distance to B squared. And right there, I know K is always going to cancel. That will happen in every problem. I can plug in the values I know. The charge of A is 40 nanocoulombs, which is times 10 to the negative 9. The distance to A is the full distance, including the 0.2 plus the x. So 0.2 plus the extra distance that we don't know that we want to find out. And that whole thing in the denominator gets squared. And on the right side, the charge of B. Again, because I have the absolute value bars, I'm going to eliminate that negative, times 10 to the negative 9 for nano, and the distance to B is just x, and we have to square the denominator. Notice since the nano is in both sides, I can cancel that piece, and now it's an algebra problem, and all we're trying to do is solve for x. I can cross multiply, I get 40x squared equals 20 times the quantity of 0.2 plus x squared. I can isolate that squared term by dividing by 20. And I'm left on the left side of just 2x squared equals 0.2 plus x, quantity squared. And now it's time to take the square root. Square root of 2, I believe, and I'll use my calculator to confirm, I believe it's 1.414. Square root of 2, yep, 1.414. I'll just do 1.41 x squared equals 0.2 plus x. Sorry, the x squared goes away on the left side. Isolate and get the x terms on the same side. And I'm left with 0.41x equals 0.2. And now I can divide by 0.41 on both sides. And I get an answer of roughly a half. X equals 0.2 divided by 0.414. And I get 0.48. 0.48 meters. So when I'm answering the question, where will it be in electrostatic equilibrium, we're going to use the direction relative to where those charges are. It's always going to be away from B. We're going to say it's 48 centimeters or 0.48 meters to the right of B. Hope that helps, and keep working on some more of these problems.